molecular orbital theory. It's a more complicated theory to describe electron bonding, but it's more powerful. Let's go back and look at oxygen. So we can draw the Lewis structure for oxygen, right? We know it has how many valence electrons? 6 times 2, so 12 valence electrons. And what we know is that we end up getting something like this. Right, hybrid orbital or valence bond theory, just like we did in the review. What's the hybridization on both O's? It's sp2, so they're both trigonal planar. So I would draw that as an O. I'd put the 3 equivalent trigonal planar sp2 hybridized orbitals around it. Each of these guys, I get a lone pair, lone pair, lone pair. That's my sigma bond, right? That would have a pair of electrons in it. And then I've got the remaining p orbitals on O. Those guys are going to overlap to form a pi bond. Right, if I look at this, based on these two models, the Lewis structure model and the hybrid orbital or valence bond theory model, they would both be diamagnetic. Right? I don't see any unpaired electrons in there. So based on Lewis structures and valence bond theory, we expect oxygen to be diamagnetic. Experimentally, though, it is paramagnetic. Here it's been put between a magnet, and you can see, maybe you can see, this looks straight down, it's starting to pull that way. It's actually being attracted to a magnetic field. So oxygen is paramagnetic. Lewis structures and hybrid orbital theory aren't enough to explain this. So we're going to use a new theory called molecular orbital theory. Theory of electronic structure of molecules in terms of molecular orbitals that are spread out over the whole molecule, right, over all the atoms in the molecule. And we make them from overlapping atomic orbitals. Right, so there's several rules to look at, and we'll think about them as we go. So molecular orbital theory is a quantum mechanical theory, which means that we're talking about the wave character of these electrons. And what we also know is that it's going to be weird. So some of the big dogs in quantum mechanics, like Niels Bohr, Richard Feynman, these guys were geniuses in this stuff. So Niels Bohr said something like, if you can fathom quantum mechanics without getting dizzy, you don't get it. Right? He was actually Danish, so he probably didn't say that exactly. If you think you understand quantum mechanics, you don't understand quantum mechanics, is attributed to Richard Feynman. So these are complicated theories that kind of make sense, don't make sense. But we have some rules that we can follow, and these rules will give us a tool that will allow us to think about different properties of molecules. So some of the rules are bonds form from interactions of atomic orbitals to form molecular orbitals. So we'll go from AOs to MOs. Atomic orbitals are what? S's, P's, D's, those kind of atomic orbitals. Molecular orbitals we'll talk about. They're going to be either sigma or pi molecular orbitals. You get a bonding molecular orbital, which is lower energy and more stable than the atomic orbitals from which it's formed. And they come from constructive interference. Electrons in bonding molecular orbitals contribute to a stable covalent bond. Anti-bonding MOs are higher energy and less stable than electrons in atomic orbitals. It comes from destructive interference of these waves, the wave character of electrons in orbitals. And the electrons in anti-bonding MOs are unstable regarding the covalent bond. So if we looked at dihydrogen, which is the simplest molecule we can form, we know the electron configuration for each hydrogen is 1s1. We have an electron in a 1s orbital. These are atomic orbitals. What MO theory says, these guys are going to come together either constructively, where they add to each other to give something stronger, right? In this wave equation, the amplitude increases, or in this picture of waves, the amplitude increases, or they can come together destructively, where they cancel each other out. And the consequence of that in terms of orbitals, molecular orbitals, is that if it comes together constructively, you get good overlap and you get a bonding molecular orbital, which would look like this. So this, because it's electron density directly between the atoms, here would be a hydrogen, here would be a hydrogen, we recognize this is a sigma bond. So we would call this a sigma MO. And it's called sigma 1s because it's made from 1s atomic orbitals. So this is bonding coming from constructive interference. Destructive interference we get a node in between. So this is a region of no electron density. Electron density will be here and here, right, on the outside of the atoms, so not between the atoms, but on the outside of those atoms. And we call this a sigma star MO, or an anti-bonding MO, right? And so following the rules, we have to take the number of atomic orbitals we use, that's the number of MOs we have to get. So we start with 2 1s's, we have to get 2 MOs, and we do. And we always get a sigma, or a bonding MO, and an anti-bonding MO. All right, so we're going to take this, and then if I put my electrons in, how many electrons do I have available? I have 2 electrons, so I'd put them both here in my sigma bonding MO, and molecular orbital theory then would predict that H2 would be a stable molecule. We have electrons in a bonding molecular orbital, and you kind of think of that as saying that these electrons will be here holding it together. All right, so just kind of watch and think. This stuff is sort of hard to explain, but it's easier to see it in action. So just watch a little bit, and I'll talk about all these things. These are the words we should be able to use about this. So again, the rules for MO diagrams is the number of MOs is always equal to the number of AOs, atomic orbitals, that are used. The number of electrons is the sum of all the electrons that you have in your molecule. Bonding MOs are always more stable, or are stable, and anti-bonding MOs are less stable. The more stable a bonding MO is, the less stable its corresponding anti-bonding MO is. And you can have 2 electrons per MO, right? That's the same thing we saw with atomic orbital theory. Orbitals can only hold 2 electrons. And we fill the molecular orbitals with those electrons from the lowest to the highest, right? That's our building up or Aufbau principle. We've seen that before. And we continue to use Hund's rule. All right, so again, I'm just going to talk about this. So what we can have is, with H2, I have 2 1s electrons and orbitals coming together. Right? If I was doing valence bond, I would draw this picture showing me a sigma bond. MO is a little more complicated, because what we're saying now is these 2 AOs come together constructively to form a bonding sigma 1s MO, and the anti-bonding sigma star 1s MO. This is typically how you draw these things. So here again, this is my atomic orbital. They have 1 electron each. They can come together constructively to give me this sigma MO, sigma 1s, or destructively to give me this sigma star 1s, right? In terms of energy, remember this is an energy diagram. So the energy of the electrons in the atomic MO are here, or atomic orbital, are here. Whereas if I put electrons down here, right, they're lower on this energy diagram, meaning they're more stable. So this is more stable, right? This sigma bonding MO is more stable than the AOs from which it was made. This sigma star MO, anti-bonding MO, is less stable. So how many electrons do I have available in H2? 2. I put them at the bottom. And again, I probably said this before, I draw my arrows like this. You can draw them like this, however you want to do it. All right, so keep watching. I'm just going to talk about these things, looking at the rules, as we said. So here's the H2 molecule again, right, all filled. Yeah, we'll talk about that in a second. All right, so here we have N2. What's the electron configuration for N? Oh, that's bad. 1s2, 2s2, 2b3. So we can either talk about all the electrons, and we are here. So what do I expect to see? I expect to see 2 electrons in a 1s, 2 electrons in the 2s, and 3 electrons in the 2p. 2 electrons in the 1s, 2 electrons in the 2s, 1, 2, 3 electrons in the 2p, right? Hund's rule, they spread out, right? Everybody, each orbital gets 1 electron before anybody gets 2. So this represents the atomic orbitals for n, 1n. This side represents the atomic orbitals for the other n. So again, we expect to see electrons in 1s, 2s, and 2p. Now we follow our rules, right? We take the atomic orbitals, we have them interact to form molecular orbitals. You always form a bonding MO and an anti-bonding MO. So here the 1s atomic orbitals come together to form a sigma 1s MO and a sigma star 1s MO. So 2 AOs give me 2 MOs. Here 2s come together, I should get another bonding MO and an anti-bonding MO. That's nice. Here I have 1, 2, 3, 4, 5, 6 atomic orbitals. So I expect to get 6 MOs out of that. 3 should be bonding MOs, right? More stable, lower energy, 1, 2, 3, and 3 should be anti-bonding. Let's look here. So this one they're calling a pi, and this is a pi, and this is a sigma. Okay, so something's going on. Then we got pi star, right, and pi star. So we expect those to be higher energy than the bonding. So this is good, right? And then we took all the electrons. So how many total electrons do we have in N2? So each N has 7 electrons. N2 then should have 14 electrons. So what do I expect to see is 14 electrons in the MO. So 2, 4, 6, 8, 10, 12. Oh, what happened here? 10, 12, 2. 2, 4, 6, 8, 10, 12, 13. Huh. Curious. That's unexpected. We should put one more electron in there. And we go right there. All right. Here is here's oxygen. And in this case, they didn't include the 1s. So they didn't include the core, just the valence. And you can do this with molecular orbital diagrams. You can think about just the valence, or you can think about the entire thing. Again, AOs come together to give me a bonding MO and an anti-bonding MO. Here we get, internet's letting me down. Here we have oxygens with this 3p. I should get 6, and I get bonding MO, bonding MO, bonding MO, antibonding, antibonding, antibonding. So that's expected. All right. Oh, here we put in our electrons. So we had how many valence electrons does O have? Has 6. So O has 6. So O2 should have 12. Let's see if we get it right here. 2, 4, 6, 8, 10, 12. Nice. Okay, and then we can write electron configurations for this thing. So instead of 1s2, 2s2, we say we have 2 electrons in a sigma 2s. So sigma 2s2, sigma star 2s2. And then we've got the next one in terms of energy be a sigma 2p2, and then sigma 2p4. There's actually 2 pi bonds there, all right? And then sigma star. So we can write like this, and we'll talk about bond order in a second. Mostly we're going to do homoatomic molecules. So molecules made from the same atoms, O2, H2, N2, that kind of thing. You can, I can't, but people can do MO diagrams for heteronuclear molecules like the HF, but it gets more complicated, right? The energies of the atomic orbitals are different, and then you have them coming together. The rules are still the same, right? So if I have 1, 2, 3, 4, 5 AOs, I should get 1, 2, 3, 4, 5 MOs. I still fill the electrons from the bottom to the top, following Hund's rule, all that kind of stuff. We will not be drawing these. All right. So we said that atomic orbitals can come together to form bonding MOs and anti-bonding MOs. Constructively, we get a sigma bonding MO when these guys are directly approaching each other, and we get a sigma star or anti-bonding MO. What we know already is that p orbitals can come together 2 different ways. So the 2px can come together, forming, right, a sigma bond, or when they're parallel, what kind of bond do they form? Exactly, a pi. So 2py would be like this, 2pz would be into the board, right? So he's going to come together and give me something that looks like this, and that would be a pi. So these are pi MOs. So the difference is we have, I'm going to do the pen, it's probably a mistake, but we have a node through here and a node that we can't see through here. So this is the difference between sigma MOs and pi. So 2 p orbitals can come together 2 different ways, as sigma MOs forming sigma bonds or pi MOs. These guys are degenerate, right? They can come together either this orientation or this orientation. You get equivalent, energetically equivalent pi bonds, which are, we say, degenerate. All right, and so this is what's happening here. I have an AO, a 2p AO coming together directly with a 2px AO. These guys come together directly like this, and we can see that's a sigma bond. So we get sigma 2p and sigma star 2p. What happens if they come together in this orientation? Now what we know is we're forming a pi bond. So we get a pi 2p and a pi star 2p, right? So here we got our 2p's coming together, right, with the nodes. We get the pi MO. The anti-bonding one has an additional node now, right? So there's electron density here, 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 and here, but there's nothing in between holding together. This is the sigma, or the pi star MO. And we put electrons in those. All right, we're getting close. So this is what we see in oxygen. Again, because we got the 3 P's, we expect to see a sigma bonding MO and 2 pi bonding MOs. All right, these X's can come together this way. These X's, these P orbitals can come together this way to form a pi bond. These ones can come together this way to form a pi bond, or they can come together this way to form a sigma bond. Sigma, pi. Where's the other one? Oh, weird. Oh, there's another kind of strange pi in there. This is a strange picture. Oof, somebody should vet these slides. All right, now we're to the writing. So we've gone over all these things. Go ahead and draw me in your notes what happens when these 2 px's overlap directly. What kind of bond do we get, sigma or pi? And it is right, sigma. So we'd get a sigma bonding MO, and then we could get a sigma antibonding MO with the node in between, right, represented by this picture. P's can come together to form pi's, right, when they overlap close like this. That would be a pi bonding MO, or you can have your pi star. So here's my pi bonding MO, and here's my pi star, right?